Welcome to the Bit-by-Bit Biostatistics Masterclass. Today we are initiating a total system override of how you view data. For years, medical education has taught you to be a human calculator, plugging numbers into formulas. But the boards have evolved. They no longer care if you can do long division. They care if you understand the architecture of truth. We are starting with Module 1, the frame. The frame is the study design itself. It is the lens you choose to place over a population specimen. I need you to understand this. If the lens is cracked, meaning the design is fundamentally flawed, no amount of perfect calculation can fix the result. Biostatistics is the operating system of evidence-based medicine. We aren't just memorizing definitions. We are learning to spot the structural integrity of a study before we ever look at a p-value. Let us build the foundation now. To tackle biostatistics, we divide our methodology into three distinct layers. First is the frame. This is our focus today, selecting the study design. You must be able to look at a vignette and immediately identify the blueprint. Is it a snapshot or is it a movie? Second is the static. These are the biases and confounders that try to corrupt our signal. Finally, we have the signal. These are your metrics like odds ratios and relative risk. Our mascot bit always says the most important pivot you can make in your prep is moving away from asking how to calculate something to asking why the researcher picked this specific design. The boards love to ask you for the next best step in study design before ever asking for a calculation. If you cannot pick the correct frame, you will never find the accurate signal. This requires a total shift in how you read every single prompt. We begin with the most basic frame, the case series. Think of this as a high-tech show and tell. You have a group of patients who all share the exact same rare diagnosis or treatment outcome. You are simply describing clinical findings. But you need to immediately look for the fatal flaw. There is absolutely no comparison group. Without a control, you have no denominator of health. You can see the disease, but you cannot mathematically prove any risk factor association. BIT says if the prompt describes 10 people getting a weird rash after taking a new pill but does not mention a single healthy person for comparison, it is a case series. This is often the very first step in identifying a new epidemic or a rare drug side effect. But remember, it is the weakest form of evidence on the pyramid. It generates questions for future research, but it does not answer them at all. Next up is the cross-sectional study. Imagine taking a high-definition photograph of a crowded room. At that exact microsecond, you can see who is wearing a red hat, which is your exposure, and who is currently sneezing, which is your disease. This is the snapshot. You are assessing the frequency of disease and risk factors at one specific point in the present time. You are asking what is happening right now. Because of this, the primary metric you get is disease prevalence. BIT says the absolute biggest trap here is the lack of a temporal link. You see the exposure and disease simultaneously, so you do not know if the person started sneezing because of the hat or if they put the hat on after they started sneezing. It can show association, but it absolutely cannot establish causality. It is cheap and fast, but you sacrifice the ability to prove what caused the outcome. Now we move into the retro filter, known as the case control study. This is the investigator, starting at the end of the story. You physically separate patients into two groups based on their disease state. You find the cases who are the sick and the controls who are the healthy. Then you look backward in time to see if their odds of prior exposure differ. You are asking what happened. BIT has a massive high-yield mnemonic for you here. Take a case to the OR. Case control equals odds ratio. Because you are purposefully selecting people who already have the disease, this is the absolute perfect architecture for studying rare diseases. If only 1 in a million people get a specific tumor, you cannot wait for a cohort to develop it. You go find those specific sick people right now and ask about their past. You control the cases, so you generate the odds ratio metric perfectly. The cohort study is the forward flow. Here you start with the exposure, which is the risk factor, and you follow the group into the future to see who actually develops the disease. This is the movie of study designs. Because you are watching the disease develop in real time, you are measuring incidence, which is the rate of new cases. BIT has another mnemonic here. Cohort equals relative risk. This is the gold standard for studying rare exposures. If a toxic factory leaks, you do not wait for people to get sick. You find everyone who was exposed and follow them. Now listen closely so the boards do not trick you with a retrospective cohort. Even if they are looking at old medical records, if they grouped the patients by their exposure first and looked for the disease later, it is still a cohort frame. It is all about the starting point. Exposure first always means a cohort. This is a review slide. Feel free to pause on this or return to it as needed. The ecological study requires you to pull out a wide-angle lens. You are not looking at individual patients anymore. You are looking at entire populations, like countries or states or cities. You might compare the frequency of COPD across different cities to see if the more polluted cities have higher prevalence rates. But BIT is flashing a massive red warning light here regarding the ecological fallacy. This is a favorite board distractor. The fallacy is measuring population data and incorrectly applying it to an individual. Just because a country has high per capita chocolate consumption and a high rate of Nobel Prizes does not mean that giving a single person a chocolate bar will make them a genius. You cannot see the individual through the population blur. This design is highly useful to monitor general population health, but completely fails at the individual level. Sometimes we need to study the actual biological hardware of humans, and that's where twin and adoption frames come in. This is the ultimate nature versus nurture experiment. A twin concordance study compares the frequency of a disease in monozygotic twins, who are a 100% genetic match, against dizygotic twins, who are a 50% match. It measures heritability. Adoption studies take it a step further by comparing siblings raised by biological parents versus adoptive parents. BIT says, the boards love asking which factor is more significant for psychiatric conditions like schizophrenia. If a child's traits are heavily similar to a biological parent they never met, the signal points to genetics. If the traits match the adoptive parents, the signal points to the environment. Let us break down our first vignette skeleton so you can see how this looks on test day. Lead in. Researchers identified 200 patients with a rare vascular tumor and 200 age-matched healthy volunteers. They review medical records to assess prior factory work history. Pivot point. The researchers started the study by separating patients based on the outcome, which is the rare vascular tumor. Discriminator. The question asks which of the following is the most appropriate measure of association for this study. BIT says since they started with the sick group, this is a case control frame. The only metric that fits this specific architecture is the odds ratio. If you pick relative risk here, you have used the wrong mathematical tool for the framework. Rare disease equals cases equals odds ratio. This logic is an absolute necessity for passing your board exam. Vignette 2. Lead in. A physician identifies 50 workers exposed to a rare, newly synthesized chemical solvent. He matches them with 50 unexposed workers and tracks their health outcomes over the next 10 years. Pivot point. This is the direct inversion of the last question. Here, the starting point is a rare exposure. They were grouped by the chemical rather than by a disease, and they are moving forward in time. Discriminator. What is the primary advantage of this study design? BIT says because we know they were healthy when we started, we know the exposure definitively came before the disease. It establishes strict temporal causality, and because it is a cohort, it allows us to calculate incidence and relative risk. Rare exposure equals cohort. Do not let the timeline confuse you. Just look at the very first step the researchers took to build their subject groups. Vignette 3. Lead in. During a single-day community health fair, researchers draw blood for fasting glucose and simultaneously measure patient BMI. They find a strong association between high BMI and elevated glucose. Pivot point. Look at the key time frames in the prompt. Single-day event and simultaneously. There is no follow-up, and there is no looking backward at old records. This is just a snapshot of a Saturday morning. Discriminator. What can be determined from this data? BIT says this is a cross-sectional study. You can determine the prevalence of the disease, and you can say an association exists between the variables. But you absolutely cannot say that high BMI caused the high glucose, because you do not have the timeline established. No timeline means no causality. This is the most common distractor answer on the boards. Always respect the limits of the frame. Vignette 05 describes a report on only 3 patients, lacking a control group. This is a case series, and its primary limitation is that it cannot establish association or causality. Final vignette for this module. Lead in. A public health study shows that states with higher average dietary fat intake have significantly higher rates of colon cancer. A physician reads this study and tells his patient that because he eats a high-fat diet, he has a massive risk of developing colon cancer. Pivot point. Pay close attention to the unit of analysis. The study looked at states and averages. The physician is applying that broad data to one single person sitting in his office. Discriminator. The physician conclusion is an example of what error? BIT says this is the ecological fallacy. The researcher has a strong signal at the population level, but you cannot map population averages directly onto individual hardware. Always match your conclusion to your original unit of analysis. This concludes the true foundation of our biostatistics frame review sequence today. Module 01. The frame has been successfully completed. We have covered the fundamental study designs, including cross-sectional, case control, and cohort studies, and their corresponding metrics, prevalence, odds ratio, and relative risk. Next, we will move on to Module 2, the static, focusing on bias and confounding.